Okay. Now the problem we're going to solve today is this. A beam 6 meter long has its supports 4 meter apart such that the beam overhangs on the right side. A uniformly distributed load of 2 kilonewton per meter is applied on its entire length along with a point load of 2 kilonewton at the overhanging end. Draw the SFD and BMD for the beam and also find the location of point of contraflexure. Okay, so this is my beam. This is very much similar to what we had drawn yesterday. Uh, Only some dimensions are different. This is 4 meter and this is 2 meter. Total length of beam is 6 meter. The value of UDL is 2 kilonewton per meter and the point load at the overhanging end is 2 kilonewton. Okay. With this data, let us start solving the numerical. So first thing, uh, like we always do, you have to find the support reactions, right? So for finding the support reactions, first thing what I do is sum of all forces is equal to 0. Then I have another condition, sum of all moments is equal to 0. Now taking the first condition, I'll put the upward force on one side because it is equal to 0. So I have RA plus RB, which are upward force. See, again, like yesterday, I said this is my assumption that they are upward. If you get the value negative, then you have to change the direction. Okay, and that is equal to downward force. I have one force here, which is equal to 2 kilonewton plus the UDL intensity is 2 kilonewton and the length is 6 meter. So 2 into 6. So that will be 2 plus 12 equal to 14 kilonewton. That is the total force acting on this beam. Now sum of moments is equal to 0. So for this I will take moment about point A. Taking moment about point A, we get, now before this I will have to write my sign convention, right? I know it, but for safety it is always better we write it down, right? So make a box like this and then this I will call it as left side, this is right side, this is clockwise and this is counterclockwise. Okay, so left side clockwise I take it as positive, the diagonally opposite to this is positive, the remaining two cells I'll put it as negative. Okay, so this is my sign convention which I am using for finding the bending moment. Now let me start. So bending moment about this point A. So I'll start from the extreme end C. Now at C I have a force of 2 kilonewton which is acting downwards. So because of this it is making a clockwise couple or clockwise moment on the right side. Right side clockwise, it is negative. Uh, I am repeating these things again and again in every numerical so that if somebody has missed, they will be able to understand. So M A is equal to minus this force is 2 kilonewton into perpendicular distance is 2 plus 4, that is 6. Then at B I have the reaction RB, which I am assuming it to be vertically upwards. So this is making a counterclockwise movement about A. So right side counterclockwise is positive. So it will be plus RB into distance is 4 meter. Correct? Now again I see this UDL is also acting vertically downwards. So it will carry the same sign as that of this 2 kilonewton. So this is negative. So this will also be negative. The intensity of UDL is 2 kilonewton per meter. Into length of UDL is 6 meter, and I assume it to be acting at the midpoint of this entire length. So that will be 6 by 2, right? So when you calculate this, and this is equal to 0, right? This is equal to 0. So when you solve this, you get RB. So let me open my calculator. I'll take the negative ones on the other side, so that will become positive. So it is 2 into 6 plus 2 into 6 into 6 by 2, or 2 into 6 into 3. 2 into 6 into 3. So that is 48, and that is equal to 4 times RB. I'll divide this by 4, so I get 12. So this implies RB is equal to 12 kilonewton. Okay. Now RA plus RB is 14 kilonewton. RA is equal to 14 minus 12, so that will be 2 kilonewton. Okay, so I will, it's okay. Now this is the value of reactions. Let me just put this on the this. I tried to use the diagram which I draw yesterday, and somehow it's not clear. Okay, now I'll write it down here. RA is equal to 2 kilonewton. This is RB equal to 12 kilonewton. Okay, so that is the reaction, support reaction. Now we will start drawing the shear force diagram. Now to draw the shear force diagram, first what I will do is I'll draw zero shear force line, the line which is representing zero shear force, right? Now this line represents zero shear force. Above this line is positive, below this line is negative. Okay. Now start from point A, right? Always start from left side so that everything comes very smooth. Now at A, I have a reaction of 2 kilonewton, which is in upward direction. So upward is taken as positive. I will draw a line, small line. Now I am assuming that, or I'll make it a little more. This is 2 kilo Newton. If possible, try to draw using a graph sheet so that it is much faster. You can draw the BMDSFT very fast. Okay, now between A and B, I do not have any point load. There is only UDL. Okay, so the intensity or the total force of the UDL between A and B is 2 kilonewton into 4 meter. So that will be 2 into 4, 8 kilonewton, right? So I'll open my calculator. First, I have plus 2 here, right? Let me just write that also. This is 2 kilonewton force. Okay. Now 2 minus 2 into 4. So that was 8. 2 minus 8 is minus 6 now, right? So minus 6 means it should be below this 0 line, right? So here it is 0. Now again, I'll just mark if this is 2, let us say somewhere here, I have minus 6. So I will just join this point and this point by a straight line, right? UDL, whenever you have UDL, the variation of shear force is linear like this, right? If it is point load, it will be horizontal. If it is UDL, it will be inclined like this. Okay. Now come to point number B. Now point B, I have reaction of 12 kilonewton which is acting upwards. Now what is the force here? This is 6 kilonewton. It is on the negative side, so it is minus 6 kilonewton. Now minus 6 and this force is upward, so plus 12. So it will be plus 6, right? So I will draw again another line which is proportionate to 12 kilonewton. Okay, so this is 6 plus 6, 12 kilonewton, right? So I will write here this as 6 kilonewton. So technically, how we because at this point I have two values, plus 6 and minus 6. So we say on the left side of point B, I have shear force of minus 6 kilonewton. On the right side of point B, I have shear force of plus 6 kilonewton. We have to explain that, right? Now from B to C, I have again UDL. Intensity remains 2 kilonewton per meter and the length is 2 meter. So 2 into 2 it is 4 and you have to subtract 4 from this, right? So minus 4, so that will be again 2. So I will just try to this approximately here, right? So I will now draw an inclined line Now this is representing the change in the shear force because of UDL. And at C, I have again 2 kilonewton force which is acting downward. So I have to show that, right? So this completes the shear force. So this is 2 kilonewton and it is 0. Okay. Now let me just show the sign. This is positive inside here. This is negative shear force, and again here this is positive shear force. Okay, so now uh, we have completed drawing the shear force diagram. You have to write also the value of shear force. So how to write it? You have to write like this. uh, Shear force diagram. uh, Shear force at point A on left hand side. Left hand side is this side. So on the left hand side of point A, I have 0, right? It is starting from 0. So I have on the left hand side shear force as 0. Shear force at A on right hand side is equal to, I have 2 kilonewton. So 2 kilonewton. Then come to point B, SFB LHS is equal to 6 kilonewton negative. So minus 6 kilonewton. Similarly, shear force on B at right hand side is equal to, I have plus 6 kilonewton, right? So 6 kilonewton. Then SFC LHS, left hand side of C, is plus 2 kilonewton, and SFC on RHS is equal to 0. You have to write like this from the shear force diagram. Now I need to find this location. I'll call this point as, I have taken this X already. I'll call this as Y, right? Point Y is at some distance from A, where I will be having the maximum bending moment, right? So I need to find this point. Now, how to find this point? For this, I can use the equation for shear force, right? So shear force at any point Y, SF at any point Y is, I don't say Y, I will just say X, right? So that is any arbitrary point X, because Y is particularly showing that point. SFX is some section between A and B, right? So I will take the shear force from here. So it is 2 minus of the intensity of shear for UDL is 2 So 2 into x, the length is x. So 2 minus 2x is the shear force at any point x, right? Now at point, I have A, B, C, I'll call this as point B. So this point is B, right? So at point B, SF is equal to 0, right? So now I am putting SFX as 0 and I'll try to find this value of y. So SF at y is equal to 0 and that is equal to 2 minus 2 into y, right? I have put the value of x as y. Now when you solve this, since 2 minus 2y is equal to 0, 2 is equal to 2y or y is equal to 1 meter, right? So at 1 meter distance from A on the right side, I have shear force changing from positive to negative and the value of shear force here is 0. That is the location of maximum bending moment on the positive direction, right? So I will have to calculate that. Fine. Now let me start the bending moment diagram. Bending moment diagram. So for finding the bending moment diagram, always you can just close your eyes and write the bending moment for the ends, right? So bending moment at A is equal to bending moment at C is equal to 0. Or I will make this as two statements because both are different conditions. So this is 0. Reason is it is a support. It is rather a end support, right? And this is free end, right? So end support means the end of the beam where I have the support. So the bending moment is 0 there unless you have a couple there. If you have a couple at this point, we will see numerical in the next class where you have a couple here. So in that case, you will have bending moment positive or negative at that particular point, right? So if since I do not have couple there, so it will be 0. And freehand, if you do not have any couple at that point, it will be equal to 0, right? So I have done this. Next I have to find bending moment about B, right? Now at B, you will have you have to find from left hand side and right hand side both because it is very typical numerical, right? So let me just find BM at B left hand side, right? Now from left hand side, or I will move this above. I'll write it here because I need this diagram. BMD BM at B, considering the left hand side. So let us start with this force. This is RA upward direction making clockwise movement on left side. Left side clockwise is positive. So 2 into distance is 4 meter, right? Then I have this UDL which is acting in downward direction. So it is making a counterclockwise movement on left side. Left side counterclockwise is negative. So minus the value of bending moment is 2 into 4 into 4 by 2, right? So I am assuming this as a point load acting at the midpoint, that is at 2 meter. So this value is 2 into 4 is 8 minus 2 into 4 into 2. So that will be minus 8 kilonewton meter. Correct? Now let me find the bending moment on the right side. BM B RHS is equal to, so here I have a point load which is coming downwards, so this will make a clockwise moment. Right side clockwise is negative, so it is minus uh, 2 into 2, right? 2 kilonewton into 2 meter distance, and again I have another UDL here for 2 meter length, so this will be 2 into 2 into 2 by 2. So I think it is going to be same, minus 4, sorry, minus 4 minus 2 into 2, so it is minus 8, right? Minus 8 kilonewton meter. Yesterday we saw where it was not like this, it was different. So it is better we cross check. Okay, so this is minus 8. Now let me go down here, I'll just put it here. Okay, I need to find uh, the point of contract. Okay, we will do that later. Now let me just draw the bending moment. I need to find the maximum bending moment at y. So for that, BM B, this point I have called it as B, is equal to, and this length is 1 meter. I have found it here, is equal to, I'll take the left side because it is small, 2 into the length is 1 meter, 1 minus the intensity is 2 meter and it is acting to 1 by 2. So 2 into 1 into 1 by 2. So this will be 2 minus 2 into 0.5. So it is 1. So 1 kilonewton meter. That is positive. So that is the BMD at point D. Okay. Now using this data, I will be able to draw the bending moment diagram. Okay. So first draw 0 BMD line. That should be fine. Okay. At A and C, the bending moment is 0. Correct? I will project this point B here. On D, the bending moment is 1. So I will just mark that value. Try to bring it down. Okay, 1 is here, and at D, the bending moment is -8, so it will be here, and here it is 0. Now everywhere I have UDL, entire length I have UDL, so it will be a parabolic curve throughout. So let me try to draw it like this. Actually, this also should have been a little curved. Let me try again. Okay, it's coming more or less straight line only. There also it will be. So this is the BMD for this particular numerical. So this is positive and this is negative. Now this particular point here, this one is point of contraflexure, where the bending moment is changing sign and the value of bending moment is equal to 0. Okay, now I need to find this location whenever you have it. So for that, I will consider a section X from A, and I need to find the bending moment at that point. So BMX is equal to, I'll take the left side. So this is positive 2 into x, right? Minus 2 into x by 2, or 2x square by 2, right? Now at x, we have bmx is equal to 0. So this value is equal to 0, which is equal to this, right? So I have to solve for x from here. What do you get? 2x minus 2x square by 2. So it will be a quadratic equation. Anybody has a calci can solve this? I can do it like this also. 2x is equal to 2x square by 2. So x gets cancelled on one side. So it will become,
Sir, x is equals to 2 or x is equals to 0.
yeah, just a minute. That's what even I'm getting here. So from this I can write 2x is equal to 4, or x is equal to 2. What did you say? X is equal to 0, or did you get 2?
X equals to yes, sir.
Yeah. So it is at the midpoint of A and B. I have the point of contraflexure, right? So why this point is important? I explained this yesterday. See, the I'll explain again if someone had missed yesterday. See, whenever you have a beam like this and you have uh, supports and the end, right? I have support like this, and I'm applying some load. You apply any sort of load on the beam tends to bend like this, right? The beam tends to bend in this way. Now what has happened is uh, I have the support here. I have the support here, and I have the load on the center also, that is your UDL, and I also have a point load in the end. So because of this, the beam is bending like this. You see this? I'll change that color. It is a wavy manner. This type of bending, which is coming at the bottom like this, if it bends like this, it is called sagging bending moment, which is taken as positive. This is called hogging bending moment, which is taken as negative. So this point is where the bending moment is zero on the beam. I'm not talking about the ends or the support, right? Any point on the beam where the bending moment is changing sign and it is zero, uh, the term contraflexure means, you see here, contraflexure. Contra means it is contradicting the flexural formula, right? So you cannot apply the bending equation on this particular section of the beam. That is the meaning of it. Okay. So this thing they may ask you in the oral also. So it is important from oral point of view. What is point of contraflexure? And also in the theory they may ask a question on this. In theory, definitely they will ask you to find the location of point of contraflexure if you get a numerical like this, right? Uh, we will